Substitutions. We're already familiar with substitutions in regular integration. I mean, consider this problem. Y is equal to integral 4x e to the x squared minus 7 dx. That's really saying that y prime equals 4x e to the x squared minus 7. And if I write it like this, then it starts to look like a differential equation. And we know the substitution will let u equal to x squared minus 7. So I have e to the u here. Of course, I don't just switch this off to be 4x e to the u. I need to differentiate my substitution. So if I differentiate my substitution, I get du dx is equal to 2x. If I substitute those two pieces into this differential equation, or I guess I'd substitute it into the integral. Let's substitute it into the differential equation. It's not the normal way we would do it in calculus, but in differential equations, that's what we would do. So this would become e to the u, and I guess if du dx is equal to 2x, well, okay, I need this y prime. I need to replace y is equal to. Now, this will be a little bit odd when looking at it in a calculus way, but I would have y is a function of x and u is a function of x. So if I differentiate y with respect to u, I would get dy du times du dx, chain rule, and that would be equal to the y prime. So I'm replacing this y prime with dy du dx. And I know what du dx is. It's the 2x. So I'm replacing y prime with 2x times dy du. When I do that, so I'm replacing this y prime with the 2x dy du, and now the 2x's cancel, and I end up with, well, let's put this down. The 2x's cancel, and I end up with another, see, my substitution really didn't solve. It doesn't solve the integral if I do it in regular calculus. The substitution itself doesn't solve the differential equation. It just gives me a new differential equation whose answer I can see right away. That must mean that y as a function of u is equal to 2 e to the u. 2 e to the u. And of course now I'm done as far as the differential equation part is solved. There's no more primes anymore, but I should put everything back into x's. So that means that y as a function of x is equal to 2 e to the what u is equal to, Control C, oh yeah, Control C, plus C, right? This should have been, when I solved it, there should have been a plus C here, so a plus C here, integration constant. Now this is exactly what we would have got if we just did normal substitution. My point in showing this before we learned how to solve differential equations with substitution is that substitutions really don't solve differential equations. All substitutions do is change one differential equation into another differential equation, but that differential equation I can solve. What's important to see here is the substitution is at least a two-part process. We make our substitution and we differentiate our substitution. Let's see some examples of this. We're actually going to study two versions or two different kinds of substitution. The first are called homogeneous, and a homogeneous equation, a homogeneous differential equation, is an equation that can be expressed as its first order, but y prime is a function of y over x. Everywhere there's a y, there's an x underneath. So this happens occasionally, and when this does happen, we can solve it with a substitution. So here's a case where I've got a differential equation. It's first order, I'm looking at this, and I recognize it as a homogeneous differential equation. Well, how do I recognize it as such? If I break this up, if I divide both sides, I can see that it's going to be so if I break it up like this, I can see that y prime is a function of y over x. It's a homogeneous differential equation. Now, how do I solve a homogeneous differential equation? What substitution do I use? When I recognize that it's homogeneous, the substitution I'm going to use then is I'm going to either, well, we can write this as let v equal to y over x, or it's probably easier to say that our substitution is going to be let y equal to v times x. So everywhere there's a y, I'm going to write a vx. I'm going to use this original form of our differential equation. So everywhere there's a y, I'm going to write a vx. Our first thing then is that's going to make this, everywhere there's a y, I'm going to write a vx. So this will be v squared x squared, v squared x squared. And I can see that the x's can cancel out. There are no more x's. When I factor an x squared out of the top, I can cancel with that x squared on the bottom, and I can see that there are no more x's. So that's a test, an indication that I really am dealing with a homogeneous differential equation. When I make the substitution, let y equal vx, all the x's cancel out, all the y's are gone because I let them equal to vx. So it really is a function of v. Y prime is a function of v. Yeah, and v is y over x. So this is indeed, y prime is indeed a function of y over x. All right, but I can't just leave this, like I've got this equals function of y over x, a function of v, but I can't leave this y prime here. Just like in the calculus example we saw, I need to differentiate my substitution. So if y is equal to vx, and v is a function of x, and x is a function of x, if I differentiate v, I get v prime. So differentiating y equal vx is going to be product rule. Derivative of the first, v prime, leave the x alone, plus leave the v alone, times the derivative of the second. The derivative of x is 1. So I'm replacing the y prime with v prime x plus v. So you always do your substitution is at least a two-part process rule. You need to differentiate your substitution. So here I am. There's a new differential equation. Now the bonus of this new differential equation is this new differential equation is guaranteed to be a separable differential equation. I know what I'm supposed to be doing here. This is a separable differential equation. I just have to go about and solve it. Now the substitution technique didn't solve the differential equation. It just swapped one differential equation out for another differential equation, but that new differential equation, I know how to solve it. It's guaranteed separable. Let's see. Well, if I'm going to use the technique of separable, then I guess instead of this y or v prime, I need the two pieces. So I'm going to write v prime as dv dx, what it is, so I can have the dv side and a dx side. I can move this plus v over to the other side as a minus v. Oh, and now I can see that if I multiply up the dx, I'm going to get a dv side and a dx side. Now well, I'm not there yet, but now I've defined my v side and my x side. So I need to get all the x's on the x side and all the v's on the v side. All right, So now all my v's are on the v side and all the x's are on the x side. As promised, it's a separable differential equation. Of course, what was not promised was that it would be an easy to integrate, or even possible to integrate, separable equation. But I do have all the v's on the v side and all the x's on the x side. We can integrate the x side. Integrating the x side is just going to be ln of absolute value of x. Integrating the v side, though, we're going to have to clean this up. So let's simplify this. To simplify this piece, I'm going to do common denominator and then invert and multiply. So I'm going to let you do this cleanup on your own. You can pause this and check to see that what I did was right, or you can trust me. Again, this is not separable technique. This is just put this into some integral form. Now, I've got a polynomial over a polynomial. I can factor this polynomial, and I'm factoring this polynomial because I'm going to want to do partial fractions on it. Alright, so with this -1 floating around out here, let's just bring it inside so that I don't forget it. Alright, all I did was from this step to this step simplify. Now I'm going to do partial fractions. Of course, the long part of this is going to be the integrate this side. The substitution part is over. The new part, the new thing that you're supposed to be learning in this video is done. It's just old, integrate this. I'm going to split this up with partial fractions. So again, I'm leaving it up to you to check this, but I just used the technique of partial fractions to break this up. Now can I integrate both pieces? Notice I could have integrated that 1 over x dx up here, but I didn't. I need to integrate both sides at the same time. So I need to set this up so that I can integrate the v side first. I'm good with the integrating the x side. Yeah, I'm almost done. I can integrate this side. That's just going to be -1/4 ln absolute value of v minus 1. It's this side here. This is an unfactorable quadratic on the bottom. So I'm going to need to complete the square. So I'm completing the square on the bottom here. That's going to be v plus 1/2. Now, I'm throwing all sorts of techniques around. Complete the square, partial fractions. If any of these seems unfamiliar, then you're going to want to look these up. You're going to want to practice these. So I think if I expand this out here, that'll be v squared plus 1/2 of v plus 1/2 of v is a whole v plus a quarter. So that'll be an extra quarter. This should be, I got to balance that. That's going to be -1/4. 2 minus a quarter is 7/4. This has got to be 7/4. Now, am I right? Well, if I expand this all out, I get back the v squared plus 2v, v squared plus v plus 2. So yes. So the hard part about this integration is this algebra chunk right here. Because I've got an unfactorable quadratic on the bottom, an unfactorable quadratic that now I've completed the square with, I'm going to try to set this piece up to be integrated with a ln plus an arctan. So let's rewrite this top piece here as 3/8 2v plus 1 and then plus an 1/8. Alright, why did I do this? Notice if I multiply this whole top piece out, if I expand, if I simplify that top piece, I'm getting the 3/4 v plus 1/2. Why did I want to do that? Because I can split it now on this plus sign. I'm splitting it on this plus sign. Okay, I got to distribute that minus across. So Now, the derivative of this denominator is, well, the derivative of the top would be, or the bottom, sorry, the bottom would be 2v plus 1, so I've got that down here, so I can integrate this piece as 3/8 ln of the bottom. It's just this piece to integrate here, and that one's going to be integrated with an arctan. So I think we're set now to do our integration. Okay, so we broke that up into two pieces. We lined this piece up nice to be integrated with a ln. I don't need absolute values here because the thing inside the ln, the argument inside the ln is positive. The other one we had is an arctan, a shifted arctan, and we already said that we could integrate that with a ln piece. There I do need absolute values, the same thing when I integrate the other side, the x side. Am I done? No. I got to put back for what v really is. So just like with our regular substitution example, everywhere there's a v, what was v? You go all the way back up to v was equal to y over x. So everywhere there's a v in here, I got to put back a y over x. Okay, now am I done? Yes, now I'm done. Hopefully the person, the asker, the poser of the question doesn't want me to solve this for an explicit solution. I'm just going to leave it as the implicit solution. So, what just happened? Lots of math. But think about it. If I've got, in general, if I've got a function, a differential equation that's a function of, so in general, if I've got this scenario where my differential equation is homogeneous, so in other words, y prime is a function of y over x, I put my substitutions in. Don't mess it up. I put my substitutions in. So everywhere there's a y, I put a vx. The x's cancel, so that's just f of v. And I have to remember, this is the thing, this is the place that everyone forgets, but you have to remember to change your y prime into your v prime x plus v. So when I do this substitution, there's my new differential equation. We promise that this is supposed to be, let's go back to here. We promise that this is supposed to always be a separable equation. Well, let's check it out. There's what I would get in general. Well, if I replace this y prime with our, I know it's supposed to be, I'm trying to show it's going to be separable, so I'm going to put in the dv dx so that I can have a v side and an x side. Let's multiply up. Well, let's move that v over to the other side first. Now I can multiply up the dx side and show that it's separable. I'm going to get a 1 over all these with v's, dv equals 1 over x dx. So that 1 over x dx side is always, that 1 over x dx side is always the same. So that's always going to integrate in these homogeneous differential equations. So there it is, it's separable. All my v's are on the v side and all my x's are on the x side. Of course, sometimes this integration with the v's is hard, like it was in our example. And then after I finish my integration, then I remember to put everything back in terms of x and y. Don't forget the plus c when you do your integration. And then we're done. Okay, so that's homogeneous. I'm saving the word, oh, by the way, I keep saying homogeneous. I'm saving the word homogeneous for when we get to linear second order constant coefficient. So they look like they're spelt the same, but we want to pronounce it differently so that we know that what we're talking about. If I'm talking about nonlinear, then I'm going to say homogeneous. If I'm talking about linear, then I'll try to say homogeneous. Anyway, that was a substitution. Here's another type of substitution. For equations of the form y prime is equal to a function of a line, so g of ax plus by plus c, a function of a line. What we do is we make the substitution, let z equal to the ax plus by plus c, let z equal to the line, do our substitution. Of course, and that will, just like with the homogeneous differential equations, produce a separable differential equation. For the homogeneous, we did an example and then we proved it in general. Let's do the opposite now for variety. Let's prove it works in general and then we'll do this example. So, if I've got an equation of the form y prime is equal to a function of a line, my substitution then is going to be let z equal to the line. Of course, I need z prime. I have to differentiate my substitution. Z prime, I'm taking the derivative with respect to x. So that's going to be a, that's a constant, plus by prime, the derivative of c being 0. When I substitute those pieces in, instead of y prime, I need to solve this for y. I need to solve this piece for y prime. So instead of y prime, I'm writing z prime minus a divided by b, and that would be g of z. There's my substitution. This should be a separable differential equation, and I guess it is, because I get z prime is equal to b g of z plus a, and I'll write this z prime then as, since I know it's going to be separable, I'm setting it up to be separable, I'm going to write it as dz dx. Now I can put all of the z's on the z side, and there is just like a 1 or whatever dx. So integrating the x side is going to be easy. Again, that's just going to be x plus c. Integrating the z side, well, that could be difficult, but it is separable. All this is showing is that if I make this substitution, a separable differential equation results. Let's try this with an example, a less involved example than our homogeneous example. So I see that it's a function of a line. So I'm going to let z equal to, here's my substitution, I'm going to let z equal to the line. I need to differentiate my substitution, so z prime is equal to 2 plus 3y prime. Let's put our substitutions in. In place of y prime, I'm going to write z prime minus 2 divided by 3. That's this equation solved for y prime is equal to this equation with the substitution in. So there, the substitution is over. The method promises me that this new differential equation is separable. Well, I can see that I can cancel off a negative 2/3 on each side. If I multiply up the 3, I'm getting z prime is equal to the secant of z. That's supposed to be a separable equation. If I put all my z's, remember 1 over secant is cosine. Now it's separated. Integrate both sides. The sine of z is equal to x plus a constant. When I integrate both sides, I've integrated the 1 with respect to x. Now that I'm done my integration, I can put back in, I can substitute back in for what z is. Z is this line. And I'm done. There's the implicit solution. If I wanted the explicit solution, I'd have to take the arctan of both, arcsine of both sides and solve for y. I don't, so I won't. Substitutions. Remember the steps. You make your substitution, and then you differentiate your substitution to swap out your y prime. And in both of these examples, the homogeneous and the function of a line, a separable equation resulted. There are other substitutions like Bernoulli that give you a first order linear, or other substitutions that give you another form, but the purpose of a substitution is just change one differential equation into another differential equation, and hopefully that second new differential equation you can solve with one of the other techniques that we learn in this course.